Okay, so now let's look at some exercises that deal with some problems that deal with these different realizations of vectors. For example, for the arrows, this is our example 2, arrows in E2 or E3 or EN. And these are all in E2, right? So it says here, find the canonical name for each vector. The vector from 2, 1 to 4, 2 in R2. Okay. Well, so this is what this means is we have the arrow from 2, 1 to 4, 2. And what is the canonical name of that in terms of the components, in terms of R2? So this is this sort of conversion or connection between arrows, like we go over 2, 1. Here's the origin. This is 2, 1 here. And the other one is 2, 3, 4, 2. So there's my arrow because it's going from this one to this one. Well, what's the canonical name? Well, the canonical name is going to be the tip is going to be 4 minus 2 and 2 minus 1 equals 2, 1. So the canonical name of this is 2, 1. It's sort of if you think of it as sort of in terms of it's the horizontal run as the x component and the vertical rise as the y component, no matter where it is. Okay. Then look at the second. So you can probably figure that out, right? That's not too hard. But then decide if the two vectors are equal. Well, you have the vector from 5, 3 to 6, 2, and the vector from 1, minus 2 to 1, 1. Well, what you have to do is you have to find their canonical names and see if their canonical names are the same, right? Because they're going to be the same if they're the same length, the same direction. And the way you can do that is by finding their canonical names and then comparing the canonical names.
Could we discuss kind of how to approach 2D if we had 2 vectors that have 3 entries?
Well, it's going to be the same way. If we have, let me say, just to do a problem similar to that, if we had the vector from 1, 2, 3 to 4, 5, 6, well, its canonical name is going to be 4 minus 1, 5 minus 2, and 6 minus 3, which equals 3, 3, 3, right? Now, if I want to know, is that the same as the vector of 7, 8, 9 to 9, 10, 11? Well, we'd find the canonical name of that, which would be 9 minus 7, 10 minus 8, and 11 minus 9, and that would equal the vector 2, 2, 2, 2. So these are not the same vector. But if I did the vector 7, 8, 9 to 10, 11, 12, then the canonical name of this vector would be 10 minus 7, 11 minus 8, 12 minus 9, sort of like keeping the components that way. And this would be 3, 3, 3, right? So this vector, so vector V1, V2, and V3 here, we'd say that V1 equals V3, but V1 is not equal to V2. So V1 is equal to V3, even though they're in geometrically different places, because they have this. Because now these numbers here. They're given. It's just like in 3-dimensional space. It's like they go over a certain x, they go over a certain y, they go over a certain z. So it's harder to visualize, right? Because you're getting into more difficult geometrical construct. So that's how you do this one here for the second problem. Okay, but here's though something that's more has to do with maybe you'd say this is a problem in calculus 3 or three-dimensional geometry. Something. Here's this is in four-dimensional space. Does the point 1021 lie on the line through these 2 points? Well, that's like, this is actually the same question as, is this vector in a solution of this linear system? These are more or less equivalent questions. So to realize this geometric question has you've actually probably dealt with a question like this in terms of whether a point, there was a point question, you had a system, is this vector? So let's see how to do this. Well, in the text, it shows you how to do this thing, but let me go and show you how to work a problem like this. The problem is that we have to use our intuition first from three-dimensional spaces. So let's just look at a two-dimensional example and say, well, we have a point, right? And we're asked, well, the question is, what's the line through these 2 points, right? We have V1, let's think of this as the first one. We have V2 as the second point here, right? And we want to, the 2 points, it's Euclidean geometry, so 2 points determine a line. So we want to know, here's this line that's through these 2 points. Well, we want to, the intuition here is we need to find a vector along this line. Well, we haven't talked about this, maybe that's, but the prop thing is, if I take the vector you want is V2 minus V1. Because I haven't, okay, this difference here is this points from tip of V1 to tip of V2. Okay, so this vector here is this one here. V2, I haven't mentioned that this is a consequence of, well, let's say, for example, if I have, to see this, well, you can see this, let's say that we have V1 plus V2 minus V1, right? What does that equal? Well, it's going to equal, see if I do, if these vectors have the right properties of associativity and commutativity, then I'm going to have a V1, a minus V2, right? And they're going to cancel, this is going to equal V2. So this one says, oh, I go to the tip here, I go from the, if I add this vector, which I don't know about, to this one, the rule is I write down V1, put this vector, the tail of this vector on the tip of this, and it's going to go here to the sum of V1 plus this. Well, where is that vector? Well, it's V2. So just by the construction of what you mean by plus here, this vector is the vector that's going along the line between the 2 points. Well, therefore, it's in, let's call this line L. Well, it's in the line L, right? So therefore, any multiple is going to sort of be parallel to V2 minus V1. It sort of stretches this one, right? So if I do 2 times this, I'm going to get a point up here, but it'll still be on this line. Now, actually, though, what we're asking is a point on this line. We're actually asking, we need real points on this line. So how do I get a point on the line L? Well, the line L is going to equal V1 plus R times V2 minus V1, such that R is any real number. Okay. Now, let's look at this. So this is the line. I start from I go to V1, I go out any positive or negative multiple of that, and I'm on a point on the line. Okay? Now, if you look at the structure of this, well, it's a particular vector plus a free variable times another vector. It has exactly the form of a solution set of a linear system. In fact, it's a linear system that would characterize this line. You wouldn't guess. I mean, this solution that I described to you is described in the text. It's not like you come to this problem and say, "Oh, this is what I should do." You know, you have to sort of see beforehand. So let's go through and apply this to this problem, right? So what this is asking is we have this. Well, we can make a vector. This point here is from the origin. It is the vector. Let's call it vector P, which equals 1, 0, 2, 1. We're asking, is this vector, is P a member of L? Right? We're asking for this particular set of numbers, this particular vector is in this set. Well, then that would mean finding an R such that it's true. What's V1? Well, we're given V1 here. V1 equals -2, 1, 1, 0. That's V1. Now we have to do V2 minus V1. Well, V2 minus V1 equals, let me see if I can move this over a little bit there. It's going to be, I'm converting these coordinate points to column vectors, is going to be 5, 10, -1, 4, -2, 1, 1, 0. This is V2, this is V1. So that's going to give me 5 minus a minus 2 is 7, right? 10 minus 1 is 9. -1 minus 1 is 2, and 4 minus 0 is 4. So let's see, I'm drawing this 2. So L here is going to equal the set -2, 1, 1, 0 plus R times 7, 9 minus 2, 4, such that R is a real number. Okay, so there's my representation. Now you'll recognize this. This could be the solution set of some linear system, right? 4 variables with 1 free variable. Okay, so we're just sort of given a lot. So we're sort of given the solution, and we're asked, is this point P in this set here? Well, what do? We have to find an R such that this combination equals this one. This is 1, 0, 2, 1. 1, 0, 2, 1 equals -2, 1, 1, 0 plus R times 7, 9 minus 2, 4. Okay. This is the formula for any point on a line. It's a particular form here. Now, this is an interesting form here because this is a vector, but this is actually, well, what we can do is we can solve this, we want to solve this for R, right? Now, if we can find an R, then we're good to go. But if there's a contradiction, then we're not. Now, this is a constant, so I'm going to subtract this from both sides to bring it over here. This is my vector algebra stuff. 7, 9 minus 2, 4 equals 1, 0, 2, 1 minus 2, 1, 1, 0, which equals 1 minus a minus 2 is 3, 0 minus 1 is -1, 2 minus 1 is 1, and 1 minus 0 is 1. Okay, so this comes to four equations, right? It's really sort of a weird linear system. 7r equals 3. 9r equals -1. And -2r equals 1. And 4r equals 1. Well, obviously, this is a problem. R has to equal -1/2. And R has to equal 1/4. So right away, just from these two equations, it would look like that this point here, 1021, doesn't lie along the line. Now, it could be that someone, I'd have to go through and check whether I've done this, this is correct. I've got -210, 510, -1/4. I'd have to check 5, that's 7, 9, -2, 4. And then we go through and we subtract this from both sides. So we'd have 1021 minus this, 1 minus 3, -1, 1, 1. So it's like there's no, we can plot the points sort of somehow, but it's 4 dimensions, so it's hard to tell, right? But this is the method you'd use. So therefore, P not on L, not on the line.
Well, it's not on the line because that's already a contradiction.
It's already a contradiction. This is like a this is really like a linear system here, but that's like 4 equations in one variable. And you notice that that it's a pretty big constraint to have the point on a line. You have to have 4 equations with one variable, so it has to be very particular points to be on the line.
So if they were all the same, if R was all the same, then
yes, they would be. So we could see that you'd have to have like you'd have to have like something like if this was like say if this was like 1, if this was like 2, then R was 3/2, then you'd have to have -3/2, and you'd have to have the right numbers here to make all of these the same, which is a big order. Okay, but that's what's going on with this. So it's like the equation, this question hides, it's like a tip of an iceberg, right? It's like it looks very simple but it's not. The technology and the whole solution isn't simple. Then here you can say, well, here's an interesting one. Describe the plane through these 4 points. Well, the answer to that is going to be a solution set to a linear system in 4 variables that has 2 directions, right? It's going to be a plane, so you're going to have some equation that's it's going to look like the solution set to a linear system with a particular point in the plane and 2 direction variables that are in the plane, so we have 2 free variables. So it's going to look like the solution set of a system of 4 variables and we don't know how many equations. Okay. Then I can ask, is the origin in that plane? Well, that's the same question as above, but it's like in a larger a different solution set. Okay. Then all these other questions are more like calculus 3 kind of questions, and they're all very similar, like intersect these 2 planes. Well, this one says that means that you have a set here and a set here, and for every pair T and S, they have to be members of the set 2, and vice versa. So they have to be the same set to be in the intersection, and that's going to give you. There's going to be a linear system you have to solve to determine that. But this is a sophisticated question, right? You're given an equation for 2 equations for planes and asked to find the equation for the intersection of 2 planes. Now, the 2 planes might not intersect, so the solution set could be an empty set. Or if 2 planes do intersect, they can intersect in a line, right? But they can't intersect in the point. So I'm gonna get either a contradiction if the two planes are parallel, or if they're not parallel, they're gonna intersect in a line, so I'm gonna get an equation of I'm gonna get another set. So the answer here is gonna be a set with one variable. Okay, so the technology, we're not gonna do a lot of stuff with this because the technology of doing this, I mean, this might be relevant to certain subjects, but this is here just to sort of like show you that these are the kinds of geometric problems that linear algebra would allow you to solve, that you otherwise wouldn't have a hope of solving if you were trying to do it geometrically. Okay. Let me